Yes,
Yeah.
yes. Very.
Okay, thank you. And welcome to the last talk of the conference. Thank you for surviving till now. So my name is Elon. This is joint work with Moni Nor and Pavel Hubacek, and it's called The Journey from NP to TFNP Hardness. So the main object of this talk is this class TFNP. So TFNP stands for Total Function NP and was introduced by Megiddo and Christus in 91. And okay, so what is this class? We saw some examples during the conference, but let me describe it. So we have the class NP, and I assume you all know what the class NP is, and this is the class of all the decision problems that are easy to verify. And what about the search version of this? So this is a class called FNP, and so in NP, if we think of like a complete problem as SAT, so the search version will be you're given an instance, you're given a formula, find a witness, okay? Find a satisfying formula assignment for this formula. And this could be a bit different from just decision. Of course, we have these reductions, but it depends exactly on the setting. And TFNP is this subclass of FNP, where it has this property that every instance has a solution. So, for example, for a set, I can give you a formula, and it doesn't have to have a solution. Okay, so this is not an example of a problem in TFNP. So if you think about it a bit, you can see that languages in NP, co-NP, the search version of them, you can actually transform them to problems in TFNP. Okay, so let's look at like this complexity zoo of the class TFNP. So it's actually pretty hard to formulate and define problems in TFNP. Non-trivial problems in TFNP. So you somehow need to prove that every instance has a solution, but your proof cannot be constructive, okay? Otherwise it would be easy. So you have to have this non-constructive proof. And so we have these subclasses of TFNP that have these nice like lemmas or theorems that prove that they are TFNP. Let me just give you one example, this PPP, this pigeonhole principle, again introduced by Christus in 94. So you have this function, and you know that its range is smaller than its domain, so there has to be a collision, and the task is to find such a collision. Other subclasses are PPAD or PPAD, I don't know how to call it. But this is like a very, I think, the most famous subclass of TFNP, since it includes complete problems like Nash equilibrium and Barrow fixed point. And we have subclasses like PLS, which is a polynomial local search, and CLS, which is continuous local optimum. But in this talk, somehow, I want to give a more generic view of TFNP and not like these particular interesting subclasses. Okay, so what about hardness of these things? Can we show hardness of any of the subclasses of TFNP? So it's easy to see that PPP can be shown to be hard if you assume you have these collision-resistant hash functions or even one-way permutations. In a recent result, PPAD was shown to be hard under this kind of obfuscation assumptions, okay, which I'm not going to define now. And in a recent paper of mine with Pavel, I've shown that these obfuscation techniques actually apply also to this smaller class CLS, which also means that you get the same results for PLS. I'm going to talk about this result next week here at the theory lunch, if anybody's going to be here. Or Pavel is going to talk about it at Soda next week, so other place you can hear it.
You're covering all bases, right?
Yeah. Where else are you going? Like, I'll make sure. Okay, so we have these results, but you can ask, okay, well, like, can I, and Christus talked about it a bit, can I show that TFNP is hard under the assumption that P is different than NP? Okay, or what else can I show here? And this leads us to the general question, what is the weakest assumption under which we can show hardness of some problem in TFNP? So there aren't so many hardness results for TFNP, and maybe there's a reason for that. And there are several barriers for proving hardness for TFNP. And one is that if you do it based on NP hardness, on the fact that P is different than NP, then you actually show that NP equals co-NP, which is not very likely. So this is one barrier. Even such a randomized reduction, okay, if your reduction is randomized, then you get the set is what's called checkable, and this is like a major open problem. So this is also another barrier. There's also an oracle relative to which TFNP is easy, but the polynomial hierarchy is infinite, okay? So this is also an obstacle proving based on languages in the polynomial hierarchy. And also recent results showing that if you try to do it from one-way functions, then maybe you can do it, but it shows that you have to have, like, your problem must have exponentially many solutions. So somehow it's not a natural reduction. Okay. Oh, this jumped too much. Okay, it jumped too much. So I want to put all these barriers and assumptions that we have when we function and everything to somehow sort them out. And the best way is to use Russell's 5 worlds that introduced in 95. Yeah. Am I right? Yeah. Okay. So he suggests 5 possible worlds where we live in. The first one is algorithmica, where P equals NP. So of course we don't have any TFNP hard problems. The second one is heuristica, where P is different than NP, but NP is easy on average. Okay, so where for any sampleable distribution, you actually solve the instances that you encore in real life, and it's very hard to find these hard instances. Pessyland is a world where NP is actually hard on average, but one-way functions do not exist. And this means that, okay, we can generate hard problems. Okay, we have a distribution to generate hard problems. But we don't have one-way functions, meaning we don't know the solutions to these hard problems. Okay, in a one-way function, you sample x, you compute f of x, which is y, and then you tell somebody to invert, so you know the solution x. And of course, one-way function is pretty much necessary for most crypto, and that's why it's called Pessyland. We have mini-crypt where we have one-way functions. Okay, we have like private key encryption and stuff like that, but we don't have public key encryption. And we have cryptomania, okay, a world where we even have public key cryptography. And I think nowadays we can add a 6th world where it's called Ophustopia, okay, where we have these very heavy machinery, indistinguishability obfuscation. Okay, and so this is even higher than cryptomania. Put it here. Okay. So we have the positive result. This is the green. So we have hardness from obfuscation. And we have hardness from, let's say, collision-resistant hash function, which is really not exactly defined, but let's say it's in a strong version of mini-crypt. Okay. And we have the barriers. Okay, of course, algorithmica, we cannot have TFNP hardness. And heuristica, we showed before that also not likely to get TFNP hardness. So Pessyland is still open here, and now I can state my result. We show a problem in TFNP that is hard based on any hard and average language in NP. Okay, so give me any language in NP. Okay, give me your favorite language like a planted click or a random start at the right threshold, etc. And you can get a hard problem in TFNP. In particular, this includes any one-way function. Okay, any one-way function implies that NP is hard on average. And our results show a TFNP problem exists in Pessyland and beyond. So if we go back, then we can also color this one. Okay, questions?
So this says something even really powerful. Like this gives a really strong hardness result for getting average case hardness from NP hardness now, right? From NP completeness. just stringing together what you said before, because if you get average case hardness from NP completeness, then you'd get TFNP hardness from NP completeness.
Yeah,
which would,
right.
Okay.
But
Very strong.
okay, but maybe that was known in this.
I mean, there's a bunch
But-
of. Yeah, okay,
I think that was already known. But.
yeah. Okay.
So let's talk a bit about the proof. Okay. So give me some language L, which is hard on average. Okay. So I have some sampleable distribution over instances for this language L. Okay. So this is my world, and this is the language L. And what is a distribution? So I have this fancy distribution D. Sometimes it gives me an element in the language. Sometimes it gives me an element out of the language. And these two cases are how to distinguish. And you can define the trivial search problem. So I just give you X, find a witness such that X, W are in like a valid witness for X. Okay? And this is, of course, a hard search problem. Okay? If it was easy, then this distribution is not hard for the language. What is the problem? This is, of course, not in TFNP. Okay? I have all these instances that don't have a solution. Okay? This is not a TFNP, it's just in FNP. Okay, how do I fix it? I don't know, let's try to make it a bit more total. Okay, let's make the language bigger. Okay, to cover a bit more. So let's take another language and like take the union or something like that. I don't have another language, I have only L. So I do, I'll take this shift of L. Okay, this is sometimes called reverse randomization, which is like a trick that has been used in the past. Each time it's differently, it's not like some generical method. But I'm going to define this language LS to be X is in LS if X XOR S is in L. Okay, so I have this like a random shift of the language. And so now I have this LS here. And now I can define the search problem. Okay, I give you X. Find me a witness for it to be either in L or in LS. Okay, this is my search problem. And I went one step further, being total. What is the problem? Okay, so I'm going to write this differently. This is X XOR S in L. Okay, this is just the definition of LS. And you can see that here we have you have an instant X that is sampled according to D. And D is the hard distribution. It's not a uniform distribution over X. D really knows where the hard instances are that are in the language and the hard outside of the language. And that's where he puts most of the weight. But here you have a random shift of D. And then you shift it to some other place. Maybe this is the easy instances, and it's very easy to find the solution. So this is not a hard problem. It might not be a hard problem, depending on D and L.
You can assume D is the uniform distribution.
Good. Okay. So how?
I wrote a paper with Leonid about that.
So, okay, yeah, that's correct. But it's not that simple. But yeah, so this is not a hard distribution. So more or less, I'm gonna explain what is happening in this paper. But okay, it doesn't just you cannot use it as a black box. Okay. But what you do is you look at the distribution D as just a function, okay? Just a function mapping the random coins that this distribution. The distribution gets uniformly random coins and then outputs some instance here. And these are all the coins that go to elements in the language, and these are all the coins you get to elements out of the language. And now I can define this language L prime, which is all the random coins that that's such that D of R are in the language. Okay, all the random coins that go to somewhere here in the language. And now I can consider here the uniform distribution because these are the random coins. And I say, okay, you're given R, find the W such that D of R and W are in this language L. Okay, and once I have this uniform distribution, then I can apply the trick from before and take this random shift S. And now I have this is distributed according to D, and now this is random, so this is a random seed, and this is also distributed according to D, and I have the distributions that I want. And okay, if you did it once, then you can do it again, and you can do it again, okay, until you cover the whole domain. Okay, this sounds very good.
To assume that you can invert this function from the uniform distribution to the hard distribution? So
I didn't assume you can invert.
I mean, so okay, so, I mean, you get this, you sample something in the...
So I think the answer is in the next slide, okay? So, well, that's a great question, even though you didn't hear the question. Okay, so is this really a hard distribution? Okay, so the instance is now the random coins that I'm giving to the distribution. And the question is, can we learn anything from the random coins about the solution? And you can think of the planted click example where you sample a random graph and then you sample a click and you sample where to put it, okay? And the random coins just tell you where the click is. So, of course, this is a problem. Versus the random SAT distribution, where you just sample a SAT at the right density, and then there's no hidden coins. Okay, the instance is more or less the SAT, and we don't think that the random coins help you in any way, at least conjectured. And so we call such a distribution public coin. Okay, the NP hard language, okay, with a distribution such that if you're given the instance and the random coins that were used to generate this instance, it's still hard. Okay, do some such distributions even exist? We show a theorem that there is a reduction from any private coin distribution to public coin distribution. Which goes along similar lines.
So why can't you just use what we did? Didn't we already do that?
No.
What? Yeah, so I don't understand.
But so there's no precise statement in the paper saying something like this, and I couldn't get one out of it, not me and Moni, and Oded pointed us to his book, and there you can get something a bit similar, but to get the whole proof, you need like a couple of exercises in his book, and also you lose some other parameters that. But essentially, yes. Maybe afterwards we can talk about it. Nevertheless, we give a different proof, okay? Which I think is also simpler and goes through the notion of universal hash functions. There was one talk talking about it, a bit about universal hash functions, one-way hash function. Okay, so now we have a public coin distribution, and but still what I have shown is that, you know, if I sample these random shifts at random, then with high probability, this new language, L prime, with all the random shifts, which is the union of all of them, is hard under this distribution. But this is not a definition of a problem. A definition of a problem has to have these S's. So I want to find them. Okay, so first the solution, let's just find them non-deterministically. Okay, so we'll have them hardwired for every input size n inside the problem. Okay, if you allow like a non-uniform version of TFNP, and then you get the hard problem. solution number 2 uses de-randomization. So we're going to use a Nissan-Wigderson PRG, and then we can actually find them deterministically and get a hard problem, okay, a uniform version. How am I on time?
We are doomed about
Yeah. Anyway, okay. So just one slide about Nissan-Wigderson PRG. So you need to assume there exists some very hard function, and then you get this pseudo-random generator, and then you can de-randomize. Okay, this is to de-randomize the search of these random shifts. So explicitly in the paper, we need to assume there's this function f in E that usually it has circuit, like exponential size circuit complexity. Here we assume you have pi2 circuit complexity. Okay, pi2 is the second layer in the polynomial hierarchy. And then you get a pseudo-random generator against pi2 circuits. And this is good because these circuits can be identified like a good shift. Okay, a good shift that really covers everything can be identified in pi2, in a language in pi2, because you need at every instance there exists a solution. And then we can de-randomize, so you get this PRG that takes log n random bits and expand it to n random bits, so you can enumerate all possible seeds. And then you get this polynomial list of suggestions for seeds. Some of the seeds are good seeds, some are bad seeds, and you cannot decide, but since you know there are good seeds, you find a way to combine everything into like one large seed, but it's a good seed. Yeah. Just one additional result that is in the paper is another connection between TFNP and crypto. So this is a totally alternative approach for showing TFNP hardness. So the result is that you can base TFNP hardness on any one-way function and some variant of zero-knowledge proof. So this is another technique for like very general technique for pushing problems in TFNP. So you have some problem, let's say even you have this SAT, okay? And you want to make a TFNP instance out of it. So, but you know the solution. So you want to tell the person, there is a solution here, but this is a TFNP, there's no promise. So we want to prove that there is a solution. So one way is just put the solution there, and then it's in TFNP because you just put the solution. But then it's not a hard problem. So you have to somehow prove that there is a solution without telling the solution, and that's how zero-knowledge proofs come into the picture. And this is also helps to get like, so the previous problem had no like structure that I can say it's somewhere. And here you can really push problems with specific structure. And we actually show that we can get more properties, such as a problem that is hard based on these assumptions that has at most two solutions. Okay, as opposed to the barrier that's saying that you have to have many solutions. Okay, so hard on average NP seems suffice to proving the TFNP hardness. Thank you.
Any more questions?
So I was a bit confused. So are you, these pseudo-randomness reduction seems to suggest that you need more assumptions than just NP is hard on average, or is it that you can deliver all those assumptions from NP is hard?
Yeah, I need this to get a uniform version. I need this like a worst case assumption. This is not an average case assumption. This is a worst case assumption that there exists this very hard problem. If you really want, if you insist on a uniform version, yes. But this is exactly the assumption. Or just assume you have such a generator. If you have a,
So this also gives you the hard function that you want, is it? You want this and the hard on average function.
yeah.
Anything else? Great, thank you.